NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hi everyone, and welcome to this very special Earth Day edition of the 2024 Von Karman series. I'm Nikki Wyrick from JPL's Communications and Education Directorate, and I will be your host for this wonderful discussion, Seeing Earth's Coastlines. SWOT satellite provides higher resolution data than ever before. NASA has monitored Earth's water from space for decades, but there's always been one stubborn observational gap: coastal sea level. The Surface Water and Ocean Topography mission, also known as SWOT, is giving scientists higher resolution data than ever before, measuring the height of nearly all water on Earth's surface from space, and providing one of the most detailed, comprehensive views of our planet's oceans, freshwater, lakes, and rivers. With our speaker, Dr. Ben Hamlington, we will learn how SWOT is #tracking world water to fill in our current gap of information regarding water at the coastlines around the globe. As a quick reminder, if we run into any technical difficulties tonight or small failures, we ask for your patience. We'll get them sorted out as soon as we can, so please do stick with us. Now, joining us as co-host today is Jocelyn Argueta, Earth Public Outreach Specialist at JPL. Hiya, Jocelyn.
Hey, Nikki. So great to be here tonight. And a reminder for all of those of you watching, this is your space program, and we want you involved in the conversation. So whether you're watching on YouTube, X, or LinkedIn, drop your questions in the chat, and our social media team will bring in as many as they can into our talk tonight. If you don't see a chat box, reload your browser, and it should pop up. And if you want to learn more about SWOT after the talk, make sure to visit swot.jpl.nasa.gov. Back to you, Nikki.
Awesome. Thank you for sharing, Jocelyn, and thanks for being here. We will come back to you in a bit for those viewer questions, so make sure to pop those questions in the chat for us. Now, our speaker for this discussion is Dr. Ben Hamlington, a member of the Sea Level and Ice Group within the JPL Earth Science section. His role as a research scientist, he focuses on sea level variability throughout years and over decades, and has also conducted considerable work on understanding sea level during the 20th century. He is a member of NASA's Ocean Surface Topography Science Team, NASA's GRACE and GRACE Follow-on Science, and is the current team lead for the NASA Sea Level Change Science Team. Hiya, Ben. It sounds like you've been pretty busy. Thanks for being with us.
Yep, I'm excited to be here. Thanks for having me to talk a little bit about the work I do.
Yeah, absolutely. So let's jump right on in. SWOT is an incredible mission, but it isn't the first mission to study oceans and sea level, right?
Right, so NASA has actually been measuring the oceans from space for over 3 decades. So when that first satellite launched, I was actually just dreaming of being a professional baseball player for the Atlanta Braves. It was just no view about studying climate science in the future. But it's this really nice success story of different missions that have built up over time to give us this really complete view of how sea level is changing over the course of the entire globe. So if you can pull up my first animation. So what we have is we call it the conventional radar altimetry. So this is the core of our satellite observations that we provide. This is the Sentinel-6 Michael Freilich satellite. It looks a little bit like a doghouse, some people say, but what it does is it sends a pulse from that satellite, a radar pulse, that travels down to the surface of the ocean, and the satellite times how long it takes for that pulse to get back to the satellite. And from that, we can actually measure the accuracy or the height of the ocean from space to an accuracy of about 1 inch, which I think is pretty incredible. So from over 1,000 kilometers up on orbit, we can make this measurement down to about 1 inch. And you can see that over the course of about 10 days, we get this complete global view of the ocean. So directly below the satellite, we have these tracks, and then we can fill in this image and get an observation of sea level almost everywhere. And I'll talk about in a little bit why I say almost. And one of the features you can see very prominent here, which we'll talk more about, is something called an El Niño. So this is a very prominent feature that affects us on a global scale, but also here in California where I am. These reds indicate where sea level is a little bit higher, the blues and yellows a little bit lower. But with this now 30-year record, you can see there the missions on the right. These have stacked up over time and given us this really nice record of sea level change from space.
I mean, that's a lot of missions. So what do we already know from these previous missions?
Yeah, so there's a couple things that we know from these missions. One is kind of focused on the local scale, and the other is more global. So if we think first about kind of regional or local, and if you pull up my next visual. So this is an image of that same satellite data that's being collected by our satellite altimeters. And this is the change that's occurred over those past 3 decades in centimeters. So those oranges and reds that you see really indicate that sea level is going up almost everywhere. So from these satellite observations, we're able to determine exactly how sea level is increasing. And the reason that sea level is increasing on these global scales, there's really 2 main factors. One is that as our increased greenhouse gases trap more heat in the atmosphere, a lot of that heat gets absorbed by the ocean, about 90% of it. And when water gets warmer, it expands and sea level goes up. The other way that sea level increases is when we have warmer water and warmer air near our ice sheets and ice-covered parts of the Earth. This ice then melts, and where does it go? It goes into the ocean. So we know there are these factors that cause sea level to go up, and we see that in this satellite data. One thing you will notice that there are some areas that are slightly redder than other areas, so sea level is going up more in some locations than others. This is because the ocean is not a bathtub, right? So when we add water to it, there's winds, there's temperature changes, the Earth is rotating, as you could just see there. So there's a lot of complicated things that dictate where that water goes when it enters into the ocean. But the overall message we can get from these satellites is that sea level is rising everywhere. And now we can think about what this means globally. So what does this mean for our, what we call Earth climate system? So if you go to my next visual, so we can take all of that data and we can average it together and come up with something called global mean sea level. So this is basically the average of all those reds and oranges and yellows that I just showed. And we can see how they're changing over time, starting back in 1993 with our first observation. And you can see that over the course of a year, you do have some slight variations in global sea level. There are shifts in water from land to ocean that cause these changes to occur. But the key message is that sea level is going up. And this is kind of where we get the oohs and ahs with this animation. It turns on its side, and you can see exactly how much sea level has gone up over the past 3 decades. And it's gone up about 10 centimeters, and so that's a few inches. And that may not seem like that impressive of a number, but later I'll talk a little bit about the context for that and why that is so important. And the other thing you can see are these wiggles that occur, right? So it's not a linear increase, it's not this flat line that goes forward and increases into the future, but there are all these ups and downs. And this is really reflective of some of those complicated signals in the ocean, these natural signals that occur on top of that background rise, one of which I already mentioned, El Niño is an important one. But we also get these changes that occur over the course of a year. So we have the movement of water due to changes in rainfall patterns from land to ocean, and that causes those ups and downs that we see. So these global observations from satellite altimetry give us this really rich information that we can use to understand not just the long-term changes that are occurring due to climate change, but also some of these smaller features that sit on top of that background rise. All right, so if you go to my next slide, now we can think about what this might mean for the future. What did these observations in this 30-year record allow us to understand about where we might be headed? So I said a little bit about an increase that's happening. You can see it was kind of an increasing line. It didn't necessarily look that dramatic of a change. But the important thing to consider is that the rate at which sea level is increasing is actually going up. So we're putting our foot on the gas pedal. So the rate at which sea level was increasing back in 1993 is about half of what it is right now today. So as that rate continues to increase, we're piling up more and more water over a shorter period of time. And one of the things we can track is the changes year to year. And an interesting thing that has happened in the past year is a really big El Niño happened. When El Niños happen, we get this temporary increase in global sea level, which you can see there, about almost a centimeter's worth of increase during 2023, resulting from that El Niño, but also because of that increase that we see due to climate change. So these factors all come together to drive sea level higher, and if we take that trajectory and project it out into the future, we expect to see, let's say, 10 to 20 additional centimeters of sea level rise in the next 30 years. So maybe almost double what we've seen in the past 30 years. That really starts to highlight some of the acceleration that we are seeing within our sea level observations.
Geez, I mean, we know that sea level is rising now, but why is knowing this information so important, and how does this matter to us?
Yeah, so it matters in a very simple way. We depend on the coast, right? So a lot of our global population lives along the coast. People depend on it for their livelihoods, for recreation. Here in the United States, certainly there are a lot of areas near the ocean where people like to go for vacation and for a lot of different fun activities. A lot of our airports are located along coastlines, and certainly our ports, where we get a lot of our goods, are located along coastlines. So it's not just those living along the coast that are impacted by sea level rise and this change, it's also those that live throughout the entirety of the world. If you can go to my next animation, one of the things that we can do is really try to understand where things are headed in the future. So I talked a little bit about that trajectory from sea level rise as we see it now, but we can then use models to tell us a little bit more about where we might be headed in the future and what kind of control we might have over those futures. So the way that we use models is that we assume possibilities of future emissions. So is there a pathway where we really limit the amount of greenhouse gases in the atmosphere and keep warming very low? We can kind of model that future and understand the sea level rise associated with that. On the other hand, is there a particular pathway where things kind of get out of control and we have a lot of additional warming? We can also model that. And that's what I'm showing here. So these columns on the right, you can see the little one all the way to the left there. That's our observed 10 centimeters of sea level rise that we have from the satellite altimetry. The next one up from that is what we expect to see over the next 30 years. That's an additional 20 centimeters or almost double. But then as we go forward into the future and think about where we might be headed by the end of this century, that's where you really start to see a separation and dependence on the amount of greenhouse gases in the atmosphere. So that middle column is a very promising future where warming is only 1.5 additional degrees Celsius by 2100, and we get a relatively small amount of sea level rise. Now, if we get up to 3 degrees Celsius, and this is our current trajectory where we are currently headed, then you start to approach 1 meter of sea level rise. Now, on the other hand, if we think about a future where warming is greater than 4 degrees Celsius, and we start to have some things happen with the ice sheets that maybe we don't expect but could happen, that's where you start to potentially bring in 1 meter or more of sea level rise. So this is my way of saying that it's really important to understand that in the near term, yes, we are kind of expecting a certain amount of sea level rise, but what happens after that is really dictated by how much we limit emissions and limit future warming as we go forward.
So you talked about it sort of on a global scale, but what does this mean locally for people living at the coast?
Yeah, so again, I made the statement that, let's say 20 centimeters doesn't sound like that impressive of amount of sea level rise. It's a few inches, right? So what does that actually mean? Now, if you can pull up my next visual. So what we can do and look at how this kind of translate on a regional scale, right? So I'd already made the point that sea level rise is not the same everywhere. So we can see exactly how different parts of the coastline might be impacted by this future sea level rise. So that same rotating globe I showed with the reds and oranges, here I'm just showing it in a different view, right? So this is the amount of sea level rise that we've seen over the past 3 decades from satellite altimetry across the globe. And again, you can see a lot of those 10 to 20 centimeters, although there are some variations, some areas a little bit higher, some areas a little bit lower. Now, if we shift that forward to the next 30 years, based on what we expect, you can see a very different picture, right? We brought in a lot of these dark reds, which is much higher amounts of sea level rise. Those white colors, those very light colors are actually very high amounts of sea level rise. So if we think about the United States, you can see the Gulf of Mexico, the east coast of the United States. Those are areas that are particularly impacted by future sea level rise that we might expect to see. If we then take a step back and think more about where we're going to be headed in 2100, so if you can do my next. So this is what those regional sea level rise projections look like at 1.5 degrees Celsius. You can click the next. This is 3 degrees Celsius. Again, this is our current pathway here, a little bit worse. And not intending to really scare you, but this is what it looks like if warming gets even higher. So if you click forward one more, you can see that these whites pretty much cover the entirety of the Earth, bar a couple exceptions. So this is really just to note that even though we know that we've seen a certain amount of sea level rise now, what happens in the future is really critical. And these satellite records we have provide important context for where we might be headed.
Wow. Can you explain what's happening in those blue and green regions?
Yeah, I'm glad you asked that. Those are there are some notable features here that have popped up, areas where sea level rise is not going to be quite as high. And you may be wondering, why is sea level projected to fall in some of these areas? And it really is a consequence of how much ice is going to be lost from the ice sheets. So those blues and greens are really centered around the Antarctic ice sheet and the Greenland ice sheet. And because we're going to lose so much ice mass potentially from those locations, it's actually changing the gravitation, rotation, and deformation of the Earth. That sounds very complicated, but really it's just changing how water is pulled towards those ice sheets. As it starts to lose some of its mass and some of its gravitational pull, the water isn't pulled quite as strongly towards it and actually spreads out into the rest of the ocean. So sea level is actually projected to fall very close to where ice is being lost. And then areas like, say, the islands in the tropical Pacific are most affected by the sea level that is being lost in those locations. I think a message here could be that maybe we should all be moving to Canada and to Scandinavia, but I do think it's important to consider that most of the Earth is going to be heavily impacted by sea level rise in some of these worst cases.
Yeah, I mean, it's good information to know. We've talked about this number a couple times tonight, this 10 to 20 centimeters. And you're right, in theory, it doesn't sound like very much, but can you give us some examples of what that might actually look like?
Yeah, so let me try to convince you that 10 to 20 centimeters is really important. So if you pull up my next animation here, so here it's a little cartoon, but it's actually using real data. So that those blue jagged line there at the bottom, that's actually a tide gauge in a Pacific island called Kiribati, a very low-lying set of islands that are heavily impacted by sea level rise and potentially future projections.
And Ben, what's a tide gauge, real quick, for those of us tuning in?
Yeah, thank you for stopping me there. So a tide gauge is another way that we've measured sea level much longer than we have with satellites. So a tide gauge, this is a very simplistic way of viewing it, and I don't want to insult anyone who works on tide gauges, but it's kind of like sticking a ruler into the ocean or along your coastline. So you're measuring what sea level is like in that particular location where that ruler is found. So these observations located along our coastlines, these tide gauges, do provide important information and actually give us a longer record as we go back in time. So satellites and tide gauges play a really nice role together and give us a good set of information. One thing tide gauges do, and you can see that here, is since they're always there in the ocean, they're not orbiting around and measuring every once in a while like we do with satellites. We can actually measure all the little signals in the ocean, all the ups and downs, all the high tides, the low tides with these tide gauges. And that's really what we're looking at here. So this is a tide gauge, like I said, in Kiribati. And that black line there is actually the flooding threshold in Kiribati. So when the blue gets above that black line, flooding occurs. And you can see that over the past 30 years, that's the record I pulled out, we've had flooding a few times, right? So a handful of times, sometimes if there is a particular bad storm or say there's a signal in the ocean that just causes sea level to be higher than it usually is, you might get to flooding location, or get to flooding conditions. Now, however, if we just increase sea level by 20 centimeters, so all we're gonna do is increase sea level 20 centimeters and we'll see what happens. So if you click forward one, now you can see with that sea level rise, those same tides, those same storms, those natural variations that weren't a problem in the past now get you into flooding conditions. So it's almost an order of magnitude increase in the amount of flooding that's going to occur. And the way to think about this, so say you're carrying a glass of water, right? And that glass of water is half full. You're not going to be too worried about water spilling over. You may jostle a little bit. It still stays below the rim. Now, on the other hand, if you fill that glass very close to the top and you start walking around, you stumble a little bit, a lot of water is going to splash over the top. And something very similar is happening in the ocean. We filled up the ocean because of the sea level rise so much that it doesn't take much of a push to get us into flooding conditions anymore. So that 20 centimeters, again, sounds like a small amount, becomes really important to affect flooding in places like Kiribati, but also here in the United States where I'm located. And if you go forward one animation, we can look at this in a slightly broader way, so not just in this cartoon form. So what we can do is look at all the tide gauges in the Pacific, right? So I'm just focusing on Pacific Islands. There's certainly tide gauges in other locations, but I just want to focus in on the Pacific Islands because it is an area very heavily impacted by sea level rise now. Each of those little dots is a tide gauge, right? And right now they're colored according to the number of days of flooding that we've seen over the past 3 decades. So this is on average. How many days of flooding on average do we typically see? And you see most of them, it's less than 10 days of flooding per year, right? Some years you may have a little bit more, some years you'll have less, but on average you have generally less than 10 days of flooding. Very similar to what I showed on the previous slide for Kiribati, which is actually one of these blue dots there. Now, on the other hand, if we increase sea level again by that same 20 centimeters, we can do this computation again. So if you click forward one, and this is what it looks like. All right, so now you have some of these red, orange dots, which starts to indicate flooding happening every other day, right? So it's a complete shift in what's happening and how it affects people's livelihoods. Their ability to go about their everyday life is greatly affected. Their ability to depend on resources of the coastline starts to become much different when you start to have this level of flooding and this frequency of flooding, again, with only 20 centimeters. And that's about what we expect, just to reiterate, by 2050. So that's about what we're expecting to see over the next 3 decades. This isn't a really far distant problem. It's something that we are dealing with now and trying to understand as best as possible with our tide gauge measurements and also our satellite observations.
What is SWOT doing to help us learn more about all of this?
Yeah, so in comes SWOT, right? So in 2022, we launched the Surface Water and Ocean Topography mission. And Nikki gave a really nice introduction as to what SWOT is doing for us. But one of the key things it's doing along our coastlines is filling in gaps. So if you can go to my next visual. It's a global, like I said, it's a global problem. Hopefully I've convinced you by this point that sea level is rising globally. It's something that's happening everywhere. And the impacts are very local. So when we start to make these flooding assessments, we really need to understand what's happening along the coastline, where people are living, and where that information is most needed. So what can we do to fill in the gaps? So previous to SWOT, we really haven't had a good answer to that, right? We do a lot of hand-waving, statistical stuff, so it works some magic, and we start to fill in those gaps. But now with SWOT, we're able to get much greater detail than ever before. So what is SWOT? So if you click forward one. So SWOT is, like I said, it's a Surface Water and Ocean Topography mission, and it's a different setup to what I showed with our previous radar satellite altimeters, right? So instead of measuring along a single track, it's measuring a swath. So it actually is able to fill in more of the global ocean in a shorter period of time than we have been able to with our satellite altimeters. So you can see how it's working there. It's sending down this pulse, and then it collects that information, develops this swath, and over the course of 21 days, we get this complete global image of the world's ocean, but also the water that's along our coastlines and on land. And I say every 21 days, but some locations actually get measured by SWOT more often than that. So here in the US, we get about 2 measurements of SWOT every 21 days. So we'll really start to getting much richer information across the globe. And one of the key things, and really the subject of what we're talking about here, is that now we're able to get measurements directly at the coast, right? So this is a big step forward. Our other radar altimeters that I talked about, they got us to within about, 10 kilometers of the coast. So not right up to the coast, just based on how that measurement was being made. Now with SWOT and this type of measurement technology, we get right up to the coast, we see that coastal interface, and then we see also the water that's on land. So here on the right, I'm showing an image of Central America and just showing some of the tide gauges that we have in this area. So those red dots are those same tide gauges I showed similar for the Pacific. And you can note there's big gaps between the tide gauges, right? There's areas where we just don't have information. I know that may seem surprising. Why wouldn't we know what sea level is everywhere along the coast? We just haven't had observations. But now if we consider what SWOT's doing, so if we click forward one, this is what SWOT is doing over the course of 21 days. So we get this complete view along the coastline. It's a little difficult to see with this particular visual, but it's actually measuring through the coastline and onto land in much greater detail than ever before. So it's just a really big step forward in terms of what we're able to understand about what SWOT is measuring. All right, so if you click forward to my next animation, so what is this actually doing for us when we think about both the ocean and then the sea level change that's occurring along the coast? So here is an animation of the actual SWOT data, so about 1 cycle of SWOT data, so that's the amount of data SWOT collects over the course of 21 days. And we can compare this to what we saw from the other satellite altimeters that I talked about previously. And there's just a much greater level of detail. These smaller features in the ocean, things we call eddies, it's kind of like ocean weather that come and go over short time scales. So those red and oranges are higher sea level, those blues are lower sea level. So this really hopefully convinces you that the ocean is not a bathtub. There's all these things happening all the time, all these different interactions at play between the atmosphere and the ocean that cause this level of detail. And SWOT is really the first opportunity we've had to see these features and be able to study them. And they're really critical to understand how our coastlines are changing, but also how the ocean is responding to ongoing warming and ongoing climate change. So SWOT's just going to tell us so much about the Earth climate system as a whole. Even though it's largely focused on surface water, we can really start to understand a great deal. All right, so if you click forward to the next animation, now let's focus a little bit on what SWOT's doing along coastlines. So I had mentioned the El Niño, right? That's an important signal that that we know is present in the ocean, can cause flooding to occur at different times, and really impacts us globally. So we were fortunate that SWOT actually, the first year of SWOT data happened at the same time that an El Niño was developing, a very strong El Niño was developing. And the full name for El Niño is actually the El Niño Southern Oscillation. And by breaking down those two terms, El Niño and Southern Oscillation, we can actually learn a lot about what El Niño is. So the term El Niño comes from actually fishermen in Ecuador and Peru who noticed that at different times of the year and some years, the water would get warmer, right? So they would be able to see off the coast of their countries where they were fishing that the water got warmer. And this usually happened around Christmas time. So it related the El Niño to Christmas, had religious connotations. So that's where the El Niño comes from, the presence of this warmer water off the coast of South America. And then the Southern Oscillation relates to pressure differences in the atmosphere, so a change in the atmosphere between the Western Pacific and the Eastern Pacific. So when you combine these two things together, you get an understanding that El Niño is this ocean atmosphere large signal that really impacts us on a global scale. So it doesn't just impact the ocean, it affects precipitation. So areas like Australia will get more or less rain depending on whether we have an El Niño or the opposite of El Niño is a La Niña. Here in California, we can get increased flooding and rain or potentially less rain than usual depending on the phase. And it can actually impact the amount of water and rainfall in the Amazon basin. And even on the East Coast, very far from the Pacific, it can impact hurricanes and storms that might be developing. So it really is this global impact. And what SWOT is allowing us to do is focus in on areas where these El Niños and La Niñas develop. Right, so around the same time that El Niño was developing, SWOT was able to fly over the coastlines of Ecuador and Peru, see that signal developing, those warmer oceans starting to develop, the higher sea level rise, and really give us potentially important information to help us understand the development of an El Niño and how it's going to progress through time and then move up the coast. And if we actually do that, so if we go to my next visual, so moving up the coast here, we're up towards California. So as that El Niño develops, those warmer waters and ocean signals develop off the coast of South America, it travels up the coastline, moves to the north, and eventually gets to us here in California. And with El Niños, we actually see higher sea levels that can cause flooding to occur. So a lot of the flooding that we see, say, in San Francisco and the Bay Area is typically driven by a combination of our higher sea level rise and also the El Niños that occur. And we could, again, see that in much greater detail than ever before with SWOT. So we're able to see right along the coastline, we were able to see these higher amounts of sea level rise over the past year, or of sea level change over the past year, and really how it can potentially affect coastal populations. We can also, as I mentioned, El Niño really affects flooding, but I want to zoom in just a little bit and focus on what SWOT can tell us about flooding that occurs in even more detail at the coast. So if you go forward one visual. All right, so this is SWOT. Again, we're going further and further, closer and closer into the coast. And here we're showing two particular time periods. The one on the left, this is kind of the northern coast of California, near Manchester, California, for those of you that know the area, and Point Arena. But on the left is just kind of normal conditions of the ocean there and tides. And you can see some of those features inland, some of the rivers, the ponds, the lakes that might be present there. And then on the right, SWOT, we were lucky enough to have SWOT actually fly over this same area when a storm was passing through. Right, so at the exact same time the storm was there, SWOT made these measurements, and you could actually see the increased water that was pushed onto the land from the ocean, but also the increased precipitation due to that storm, and we could start to pick out flooding that's occurring. And to be able to do this on a global scale is really important information for coastal communities. We're able to not just tell you that sea level is rising, but now we can start to potentially track flooding, better understand where that water goes as it gets onto coastal lands and how it might change over time. So again, really important information that we can now start to provide with SWOT, improve our scientific understanding, and turn that into something that benefits coastal communities.
I mean, that's some incredible detail that SWOT can measure along the coastlines, the oceans, some more inland water features, but what else can SWOT do?
Yeah, so I focus very heavily on the ocean and coastlines here, but SWOT is actually measuring, we say, nearly all surface water on Earth. There are some very, very small features. It's not going to see your pool in your backyard, for instance, and it also doesn't measure at very high and low latitudes. But SWOT is giving us a really nice view of surface water as well, and water on land. So if you click forward one animation, what I mean by this is that SWOT can measure rivers, lakes, and reservoirs on a global scale with even greater detail than ever before, right? So here is just one little example. So we're staying in California, but this is Death Valley. It's actually the lowest altitude land in the United States, and it's typically does not have water in it, right? It's a very hot place, very dry place, doesn't typically have water. But because of some of the storms that we've had here in California, we had Hurricane Hillary, the remnants of Hurricane Hillary impacted Death Valley back in 2023. It actually led to the appearance of, we call it an ephemeral lake, a temporary lake in Death Valley and Badwater Basin specifically. So again, it's not something that's always there, but SWOT allows us to see these types of features when they pop up and track them over time. So over the course of the next few months, there were other storms from atmospheric rivers and other storms that impacted the coastlines of California that then went to Death Valley. And you could see this change occurring over time in the depth of the water found in Badwater Basin. And there were a lot of images and news reports about people going out and canoeing and kayaking and things like that in this water. But we were actually able to estimate the depth using SWOT by understanding the elevation of Death Valley. Again, we know it's one of the lowest altitude places in the world, and differencing that with the SWOT observation, we can actually see that the depth of that water was on the order of a foot to 3 feet. So incredible detail all the way up from space, and really rich information that we can provide in a way that we've never been able to before.
What can you tell us about SWOT's first year and its incredible team? It's doing such great detailed work, but what about the team?
Yes, so there is a large international team that has been working on SWOT for decades. So going back a couple decades, I think the first idea for SWOT was almost 2 decades ago, the first meetings about it. I certainly wasn't involved in that, so full credit to those that were working on it. But over the course of 2 decades and into this first year, it's been a real team effort to collect the data, understand it, because it's a completely new type of data than we've ever had before, and really be able to turn that into something that is useful both for science, but also for those that might need information on water living around the world. And very recently, all that hard work from the team culminated in the release of some of this data publicly. So anyone listening to this now can go and download the data. You can draw a little box around your town or your favorite lake or river or part of the ocean and download the data and start to look at it. So I think it's been a real success story for this team, and the hard work certainly continues, but I think we've made a big step forward. And if you go to my next visual, I think just to note that this is a real paradigm shift in terms of our ability to monitor surface water from space. It's such a new frontier that SWOT provides. I think I've only scratched the surface of what it will support and what it will do for us as we move forward. And I'm certainly excited about what's to come, and especially to see all the cool results once people start getting their hands on the data.
Thank you so much for sharing all this phenomenal work that SWOT is doing. Jocelyn, I know the audience has been asking so many great questions. Tell us, what are they asking for Ben?
Yeah, lots of really great questions coming in from our audience. Zoo on YouTube wants to know, can SWOT data be used to map freshwater lake data, for example, the Great Lakes?
Absolutely. Yep. So SWOT has already provided some awesome data of the Great Lakes. I think let's say roughly every 10 days, you're going to get a really nice overflight of the Great Lakes from SWOT. And indeed, it can do that at basically any freshwater lake, as long as it's big enough. But we can really monitor the full expanse of surface water found in our lakes and reservoirs using SWOT. So definitely can definitely see something as large as the Great Lakes and provide really good information on the water levels there.
And Monkey Bits on X asks, just wondering the level of detail your cameras have. Is it a live feed? How many pixels? How many terabits per image?
So this is referring to, presumably it's referring to the SWOT. So they're not certainly not cameras. It's a slightly different technology. So we're actually sending a radar pulse down to the surface of the Earth and timing how long it takes to get back. We do have other satellites that actually provide an optical or take a photo from space and allow us to see in that way. But this satellite does something a little unique. It's actually measuring the height of the ocean by measuring the time it takes for a pulse to travel to the ocean and back to the satellite, which I think is kind of mind-blowing to be able to get that level of detail without observing it directly with a camera or something like that. I think it's really cool and a testament to the great engineering that the SWOT team does.
Such an incredible mission. Mrs. Ort on X also wants to know, how are the deeper ocean currents, the conveyor belt, being affected by warming?
Yep, that's a good question. So we hear a lot in the media. I think every other week there's a story in the Washington Post about the collapse of the AMOC, the Atlantic Meridional Overturning Circulation. For those of you that have seen The Day After Tomorrow, that's actually the starting premise of that movie, is that that conveyor belt has broken down. But it is something that we are able to measure. We are able to understand the changes that occur, not just from sea level. Sea level is certainly an indicator of that, and the ocean height changes I'm talking about here. But there's so many other types of observations we rely on, including understanding at depth how things are changing. So we actually have buoys, they're called the Argo buoys, that actually travel down to depths 2,000 meters or greater, and then can measure the temperature and salinity of the ocean as we go up through the water column. So this is my way of saying that the satellites I'm talking about here form the part of a larger observing constellation that we rely on to actually track things like that overturning circulation. And I guess the one other note there is it's still it's a research topic. We're still working on it, and I think it's something that we shouldn't necessarily overreact to in the media while scientists continue to research it and we continue to observe it.
And Christopher on LinkedIn is wondering, can you correlate the rise in sea level with the shrinking of the ice sheets?
Yes, we can, and that actually brings in another great satellite that we have here at NASA, the GRACE satellite and the GRACE follow-on, its successor, actually are able to measure mass changes on Earth. So it's a really cool concept where you have two satellites that are essentially tracking each other as they orbit the Earth. And all they're doing is measuring the distance between those two satellites. And the way the satellites the distance is affected by the gravity or how massive something is on the Earth below them. So there's this constant interplay, I think I've referred to as like a Tom and Jerry chase between these two satellites that allows us to measure the ice sheets and how much ice is being lost in great detail and track that change over time. And we do find that the ice being lost along with the warming of the ocean, it does start to add up to our total sea level rise. So we don't just measure the sea level rise, we also measure why it's changing and what are the causes of it.
Christopher on LinkedIn wants to know, you've talked about the world's ocean not being a bathtub with all the variables involved. Can the ocean be considered a closed loop system?
Well, that's a good question. So I think that you could frame it that way with some assumptions built into it in terms of the connection between like the ice sheets. We do a lot of pumping of groundwater, so water that gets pumped out of the ground might not necessarily find its way back into the ground. So some of the changes that are increasing or that are happening in the ocean, you can kind of perceive them as permanent. And the reason I say assumption is that there are different timescales, different things that are happening over the course of days, years, centuries, and so on. So Yeah, I guess the short answer to that is you can consider it a closed loop system with some important caveats as to inputs of water.
And Bianca Pinto on YouTube says, this is amazing. How do you envision using this data to project to the different water scenarios for the 1.5 degrees, 3 degrees warming scenarios?
Yep. So right now, some of you may have heard of the IPCC assessment report process. So it's this big global process to generate information across our climate system. And our sea level projections really come from that effort, that global effort. And one of the big findings, or let's say big limitations with the sea level projections that came out of the 6th assessment report in 2021 is how close to the coastline we could actually measure sea level and then project it with models. So it's one of those simple things that if we don't observe it and we don't understand it, it's very difficult to model it. So now with SWOT, we're going to be able to observe it, improve our understanding of it, and then build that into those same models that are relied on for these large-scale international assessments. So a lot of work to be done, but it's a starting point, right? We now have our eyes on the problem.
Definitely. Space Opera on X is wondering, is there a planned use of the sea level data? They're interested in seeing an online tool that correlates to a zip code indicating years. What do you think?
Yes, so there is a lot of work being done, and I think more than ever within NASA, we're very focused on what we call open science. So that means not just providing the data, so it's not just open data where you can go click a button and download the data. It's trying to be able to support use of that data, and that's really what open science gets to. So there are teams here that are developing tools to make that data easier to use. Given the high level of detail that SWOT supports, I fully expect we'll get to the point where you can zoom in to a particular location and see, again, track your favorite river, lake, or reservoir. I don't know if anyone has a favorite one of those, but you'll be able to track that kind of thing in great detail with SWOT, and I think we're working to build the tools that allows anyone to do that.
IGY1 on X is wondering, is there hope?
So in general, yes, of course, there's always hope. Yeah, and I don't, and specifically about, certainly about sea level rise, I think there is a lot of energy to address the problem, and I think a hopeful message here is that we now have tools and information that we can provide to people who are doing that work. So instruments like SWOT, our other satellites that I've mentioned here, it's really detailed information that rises to the level that we need to respond to the changes that we're seeing across the climate system. So I am hopeful given the scientific progress that we're making, and I think that the pieces are there, right? So we're going to continue to do what we need to do on the NASA side to ensure that everyone has the best information that they need.
We'll get in deep with this tonight, Ben. Thank you for that. We've got time for one final question, and we've had so many, so I'm sorry to cut us off. But Jocelyn, our final question for Ben tonight.
Yeah, it looks like there's some aspiring scientists in our audience. Ted on LinkedIn wants to know, hey, Ben, you're so knowledgeable. What can I do so I can grow up to be a climate scientist just like you?
Yep. So I kind of backed my way into climate science. I was an aerospace engineer by training. Really wanted to come and build really cool things, like a lot of people here at JPL do. But once I started looking at some of the data from the satellites I was studying, like these satellite altimeters, I realized how important this problem was and how critical it is to understand the changes that are occurring with our climate system. And that's my way of saying that there are so many entry points into climate science, so many needs that we have to try to understand the scope of the problem. An aerospace engineer certainly can study, develop the tools that allows you to study climate science. If I just think about the meetings I've had today, I've met with geologists, oceanographers, social scientists, people who work with data visualization, education outreach. I mean, there's so many different areas where we have needs within climate science. So there are such a diversity of entry points. I would say do what you're passionate about, and if you're passionate about climate, I think there is a path for you to get into climate science and develop the skills you need to study in this area.
Very inspiring. That is all the time we have for today. I want to thank our speaker, Dr. Ben Hamlington, for joining us to celebrate this amazing mission SWOT and all the gaps it's filling in our understanding about coastlines and sea level change. Also, thank you to our wonderful questions co-host, Jocelyn Argueta, and for everyone working behind the scenes to make this possible. Thank you to all of you. I also want to thank all of you watching and joining us for taking the time to join with us and watch every month. If you'd like to revisit any of our past Von Karman talks, please visit JPL's YouTube page. And do join us next month for Shake and Bake, how spacecraft are tested to handle the harsh environment of space. In the very kind words of our speaker tonight, there is hope, thanks to SWOT and all the incredible climate science that is happening. Thanks again for joining us, and we will see you all in May. Bye.